All right. Can everybody hear me? Okay.
Yes. Yes.
All right. Let's jump, and you can still see the screen full size. Perfect. All right, let's do this then. So let's jump back into where we were yesterday. On yesterday, we talked about the Grignard reagent, and today we're going to talk about what's today? I'm still in February. My bad. Today we're going to talk about the Gilman reaction, and I want to put a. Let me throw a blank page in here so I can give you a brief, like a generic overview of the Gilman, and then we're going to come back to those examples. All right. With the Gilman, it's a little bit different from the Grignard. Hold up. Pick a better pen. So I talked about already how to make it, right? The way you make the Gilman reagent, you take two equivalents or 2 moles of a organolithium species, let's say CH3Li, methyl lithium. You react that with copper iodide, and then what you get out from that is this copper species where both methyl groups are attached to copper. Again, copper is negative, and then lithium here is positive. Sorry about that. This is a huge program, so that's why it took so long to load and start and all that. But I'm about to close it. Poof, pow, be gone. Come on now, get out of my way. It chews up a lot of memory when it's open. So that's the Gilman plus you have a lithium salt because remember you use two parts of that organolithium. So both of those methyl groups get attached to copper, and then one of those is uh, one of the lithiums is with copper as a salt. The other one goes with the iodine from copper to make a salt. But this is insignificant. We don't use that at all, right? So this is the Gilman reagent, and let me show you how the coupling part works. And then when I show you that, we're gonna go back up and look at those examples. So to use a Gilman reagent and a coupling, uh, we just it's the same concept that we talked about when we used the Grignard, right? So I'm going to take that same Gilman, right? So that's that, and I'm going to just react it with uh, that, right? I want you to understand a couple things. Let me put a couple of notes here. For the Gilman reagent, it can react with any type of alkyl halide, aryl halide, vinyl halide. It works with all of them, right? And then the Gilman itself, just like a Grignard, it can be alkyl, aryl, or vinyl. Y'all remember that from Monday? Let me go back up right quick. When we talked about the different types of Grignards that are available, right? You can make any type of Grignard, and you can use any type of halide or something with a good leaving group like a triflate or something like that, right? So let's go back to here and let me show you a couple of key things about this Gilman reaction. So when the coupling takes place, right, only one of these groups is going to get transferred to couple. So I'm going to circle this one or box it in. So only one group transfers, right? And so in the product, what you're going to see So I can move this over. All right. So in the product, I'm going to have this, like that. Right. That's my coupling product. Let me zoom in and fix that three. So this is my coupling product. All right. And then plus what's left of the Grignard. I'm sorry, of the Gilman reagent. So you have this. So this copper species, right? Plus lithium bromide. All right. That's what's left. And let me fix that because that looks sloppy. If you have a question, don't I can't see the chat, so just unmute and ask it. All right. So this is the coupling product right here. So that's one of those CH3s came from the Gilman, and then the other one stayed with copper. That's one of the drawbacks too, because you end up wasting those groups, which we call ligands. You end up wasting them because once you get to here, this is useless, right? This is dead. It can't go back and couple with another arrow halide or alkyl halide, right? Once you get to this point, this is dead. So you can't do another reaction. All right. Any questions about that part, or about anything? And again, if you have a question, just unmute. You don't have to worry about. Don't put it in the chat because it's not popping up.
So if there were 2 moles of the copper lithium, then you'd be able to do 2?
You mean if you use two moles of the Gilman?
Mm-hmm.
Sure. And again, keep in mind, you have one. Even if you do 1 mole of the Gilman, it's still like Avogadro's number of those molecules. You understand what I'm saying? So you can still have
All right.
multiple reactions happening, but once
Okay.
that copper gets used up, then it can't go back. So normally, when you use a metal in a reaction, it
Mm-hmm.
it goes through what's called like the mechanism. You describe it as a cycle. Like the metal is basically it's like a catalyst. It goes
Okay.
through the cycle. It does what it's supposed to do, and then it comes back around back to its original state, and then it does it again. But when you're using something a reagent like this, that doesn't happen. Once it transfers that methyl group, it's done.
Okay.
Good question. Very good question. All right. Any other questions? All right. Let's go back up to here and let's look at that second example. Sometimes you'll see your Gilman reagent written like this, right? You have the two groups that are attached to copper in parentheses with a subscripted two, but it's the same. It doesn't mean it's the same reagent and it's going to do the same thing. It's just written a little bit differently. All right. So look at those two. Let's use our strategy. Find CM, find RX, and then put C and R together. That's the strategy that we use to do this reaction. So where is RX?
Where the benzene and iodine is.
Good. Right here. Right. This is, I got to zoom in on it a little bit. This is RX, right? X is always your leaving group. And sometimes it may be a different leaving group. It won't necessarily always be iodine. It can be a triflate. It can be a tosylate. It can be uh, like an oxygenated leaving group. But the X part is always your leaving group. So you don't have to, worry about where how to find it or where it's going to be. And then what about on the other side? Where's CM? This is very important too because that helps you to understand when you construct a product. That helps you to understand how to put that product together. So what is M? What do we say the M represented?
Metal.
The metal. So where's my metal? It's copper, isn't it? Right? Because we're looking for the
Yes.
organometallic part. Like, so if you're thinking about being the metal being, yes, lithium is a metal, but it's not the organometallic part. It's not the metal that's connected to carbon, right? That's what we're looking for. So this is my metal right here, and then that's my carbon. So, right, so let's do this. This is the carbon that's gonna connect with this carbon. Are y'all following that? And notice the temperature, minus 78. A lot of your organometallic species are really reactive, and so if you don't keep it at low temperature, then they end up decomposing, and you can't really use them. All right. So what is my product going to look like, and what's going to be attached to what? So let's start out here. Let's do it in black. Let's start out here. Come on, man. I can't find my little glove. I bought a glove to keep my palm from touching the screen. I can't find it. Ain't no telling where it is. I can zoom in on that so I can write it out. Right. So remember, this is this carbon right here, where that iodine was. That's the carbon that I'm making a bond to. So I'm gonna go ahead and draw that bond out. I'm not gonna fuse them together. Right. I need that bond to be shown. Right. And then on the other carbon over here, how many carbons are in that chain? If you start counting from where that pink dot is.
3.
3 carbons. All right. So over here, those same 3 carbons are gonna be right here. So I'm gonna put that pink dot back so we'll can see that. So that's that. That's 1 carbon. And then here's my second carbon. And then here's my third carbon. So it's still a 3 carbon chain attached. Are y'all following that or no? Plus this Cu. And then what is it? Lithium iodide. Plus lithium iodide. Hold up, let me fix that part. Yeah. Plus lithium iodide. Anybody not see what we just did? Like you can imagine these are or go ahead. You can imagine these organometallic coupling reactions are extremely powerful tools, right, for making uh, carbon-carbon bonds. Fast, uh, really mild conditions, efficient, high yielding, and that's what you look for when you're doing an organic reaction. You want it to be a high yielding reaction that's efficient and that's done as under the most mild conditions possible. Um, all right. Any questions about the Gilman?
How did you get the second one with the copper?
Okay, remember over here, you got two of those groups attached. But remember, only one of them is going to transfer, and the other one stays with copper. Right? So if I were to draw that out, let me squeeze it in here. It would look like this, right? Three, 1, 2, 3, like that. Just like we had it shown down in the other example. And so when you that's the again
Okay.
one of the key concepts or key ideas behind the Gilman is that only one of those groups is going to get used, right? So we'll transfer one, and then one stays with copper. Good question.
Okay. Thank you.
Mm-hmm. Any other questions about that? Oh, sorry about that. So if you look at the example underneath that, that's not a Gilman reaction per se. What is that reaction underneath there? What would you get from that? Anybody? You got 2 moles of a organolithium plus copper iodide. What should we get from that? I'm gonna shrink this so I'll have room to draw it. And this, what do I tell you? All right, don't all speak out at once. Now there's gonna be a big gap on this video of silence. Right, those conditions that are shown that's the way you make the Gilman reagent. That's how you synthesize it. You actually take 2 equivalents of an alkyl lithium or organolithium, and then react it with copper iodine. So what would the Gilman look like? What would that Gilman look like on the other side of that arrow? You know it's going to have copper in it, right? So it's going to have a copper. Let me try to do that. It's going to have a copper atom. You know it's going to have a lithium. And then you know it's going to be lithium iodide because you start out with a copper iodide. But what's attached to copper? That's the question. Yeah, the whole group, right? All this whole thing, all of this. Let me just highlight it. From this carbon, right here. Let me make that carbon a different color. Right, this carbon right here. That's the carbon that's going to end up bonded to copper, and everything that's attached to it. Right, so you're over here. We can write that in. And it's going to be 2 of them attached, not just one. And then so here, the same carbon, boom, like that. Right, there's all the point. The key point is right here. That there has to be a covalent bond between the metal and carbon. That's what makes it an organometallic. So that carbon that's over here highlighted in yellow is that carbon that's attached to copper. So this is the synthesis of a Gilman reagent. All right. Any questions about that or about anything we talked about so far? So here, let me give you the scope right quick again. Let me add a page in there. And I'll go back to that if you were still writing it. I'll go back up to it in a second. Right, so the scope of that Gilman reaction, your organolithium can be anything, right? To make it. It can be an aerolithium, it can be a vinyl lithium, or it can be an alkyl lithium. Any one of those plus copper iodide is going to give you a Gilman reagent, right? And of course, it's got to be 2 moles. Sorry about that, man. This stylus. I was doing good with this thing at first. All right, so you end up with this. I'm just gonna right, or this, or this. Right, all of those can be used to make Gilman. Mhm. All right, questions? Any questions? And then of course the Gilman can react with the same, right? Aryl, vinyl, or alkyl. Let me go ahead and put that in here. So this is aryl. This is vinyl, and this is alkyl. All right. All right. Any questions about anything so far? That, that you on copper is ugly over here. All right. Question? Any questions about anything? Let me put this down here. Right, so it can react with any one of those, aryl halide, or alkyl halide, or vinyl halide. All right. Let me introduce you, unless there are questions. If you got a question, you can unmute and ask it. So one again, let's kind of recap this. One application of the use of alkyl halides is to make organometallics. Right? We talked about the alkyl halide, how to make those, and now we're talking about how to use them. And so one application is making organometallics, and then the other part of the organometallics, why make those? Well, you can use those to make carbon-carbon bonds and coupling reactions. So we just saw that. And then so one other application is the use of organometallics to make alcohols, right? So what happens when you use organometallics to make alcohols is you react them with carbonyls. I'm gonna give you a generic example before we jump in too. All right. So let's talk about that real quick. So addition of, I'm just going to abbreviate that, organometallics to carbonyls. Right. So in a generic sense, if I take a aldehyde like this plus, let's say, a granular, and let me write this a different way because I want to make a point about the order of addition. Uh, Here you add in the granular, and then in the second step you add in some acid. Let's say acetic acid, right? The second step is the proton transfer, right? That's where you're going to form your alcohol. So in the first step, I'm just going to write this is I'm not writing the mechanism. What I'm writing out is the stages or the stages of the reaction. So after the first step, you're going to get this, and we're going to talk about the mechanism in a minute. O minus CH3H, and then on that oxygen, that's going to end up forming a salt with your magnesium or whatever your metal is. So oxygen is negative, the magnesium is positive, like that, right? And then, so you'll notice over the arrow that says one. So what you do, the way this works is you take your aldehyde, you run it in whatever solvent you're using, ether minus 78, and then you syringe in your granular, or you transfer in your granular, usually through like a cannula. And then after you add in your granular, you stir that, and you get this uh, alkoxide intermediate. And then at the end of the reaction, you treat it with an acid. You treat it with some type of acid, right? And all that acid is going to do is put a proton on your alcohol, on your oxygen to give you the alcohol. And then let's say, I'm gonna put an X here because I want to make a point about this too, because that's a common question. So your acid is always gonna have a conjugate base, so that's what X minus is. That's your conjugate base, right? So here you're gonna get OH like that, right? That's your alcohol that you get out, and then whatever that conjugate base is of that acid is gonna end up with your magnesium. So it'll be that plus, I'm gonna put the bromine over here. I'm gonna highlight that part. Right, that whatever that conjugate base is from the acid, it ends up with magnesium. Right, everybody remembers conjugate base, conjugate acid, all that stuff, right, from part one. take that silence as meaning maybe. I'm not gonna say no. All right. So that X from the acid is always going to end up with your magnesium, whatever the conjugate base is. So whatever the acid you're using, the conjugate base, boom, it forms a salt with magnesium. It doesn't matter because it's trash anyway, right? You end up throwing it out in the workup. But this is the most important part right here, right? So when you add an organometallic to a carbonyl, you can make alcohols, right? So this can be a ketone, it can be an aldehyde, it can be a ketone, or it can be an ester. All right. One of the things about this section and the sections going forward is you got to remember your functional groups. So if you don't remember them, then you're going to need to refresh yourself on them. Because I promise you, when we're talking about these reactions, the functional groups are the basics. So you got to get past that part before you can understand the more intricate parts of this stuff. So you gotta have a working knowledge from part one, and part of that working knowledge is knowing your functional groups. So if you rusty on that, hopefully when you took part one, if you took it from me, you made those flashcards that I told you to make. You can go back and refresh yourself. And if you didn't make flashcards, there are a million websites with functional group flashcards that you can download from. All right. Any questions about the carbonyl addition? I'm gonna send videos on this topic later on today. So be looking out for that and make sure you watch it for Wednesday. I'm sorry, Friday. All right. Any questions about anything? All right, no questions. All right, let me see if I can figure this out. All right, let me stop this recording right